First, we're going to meet our enemy, the hardware itself. Then, we'll try to get a real gut feel for the insane differences in speed inside a computer. After that, we'll face down the two biggest ways our data can get destroyed during a write. We'll forge our first weapon against them, a checksum shield, and then, critically, we'll test it to make sure it actually works. Finally, we'll see what we've accomplished and what monster is still lurking. Okay, first up, the hardware adversary. To build something truly reliable, you have to start with a healthy dose of paranoia. You can't think of the physical hardware as your friend. You have to treat the world of silicon and magnetism as an opponent, a clever one that you constantly have to outsmart. So, now that we've identified our foe, let's talk about the first major rule it forces on us. And that rule is all about speed. Or more accurately, the absolutely massive, mind-boggling gaps in speed between different parts of a computer. We're not talking about small differences here. It's a grand canyon of latency, and it dictates almost every single design decision we're going to make. To really wrap your head around this, let's use an analogy. Imagine your computer's CPU is a hyper-fast chef, and a single operation takes one heartbeat. Okay? So getting data from its L1 cache is like grabbing an ingredient that's already in its hand. Instant. But what about getting it from RAM? Well, now the chef has to take a 5-minute walk to the pantry. And getting it from a modern SSD, the chef has to stop cooking, get in a car, and take a 2-day road trip across town. A spinning hard drive? That's a flight to another continent. It's just an insane difference in scale. Now, that analogy might sound dramatic, but honestly, the real numbers are even crazier. Look at this. Getting to RAM is about 200 times slower than the L1 cache. But going to a fast NVMe SSD is about 1,000 times slower than RAM. That means while the CPU is waiting for just one piece of data from the SSD, it could have executed literally millions of other instructions. It's just sitting there, bored, waiting for data to arrive. So why are they so different? Well, a hard disk drive is a physical, mechanical thing. It's got a spinning platter and a little arm that has to physically move to the right spot. That movement makes random reads and writes painfully slow. An SSD, on the other hand, has no moving parts. It's all flash memory, so random access is way, way faster. But it has this one really weird weakness, this Achilles heel, called write amplification. And here's the key thing to understand about SSDs. You can't just change one tiny piece of data. Think of it like a whiteboard. If you want to change just one word, you can't just erase that word. You have to take a snapshot of the entire board, erase the whole thing, and then write everything back, but with your one word changed. That extra work, that read, erase, rewrite cycle on a much larger chunk of data, is write amplification. It creates hidden performance costs, and it actually wears out the drive over time. So, because of all these weird physical limitations, we're forced into a fundamental design choice. We just can't work with individual bytes when we talk to a disk. So every database on the planet organizes its data into fixed-size chunks called pages, usually something like 8 or 16 kilobytes. From this point forward, the page is our atom. It's the smallest chunk of data we ever read or write. It's all or nothing. Okay, so we've got a handle on performance. Now let's pivot to the really scary part, reliability. What happens when the physical world decides to attack our data? When we try to write one of our pages to disk, there are two absolutely catastrophic ways it can fail. We call them the twin dragons of durability. The first dragon is the torn write. This one's brutal. Imagine you're writing an 8 kilobyte page, but the power cord gets kicked out of the wall when you're only 3 kilobytes in. What's left on the disk is a corrupted mess, a Frankenstein's monster of a page that's part old data, part new data. The second dragon is the partial write. This is more subtle. Let's say you successfully write page A, but the power fails before you can even start writing the related page B. The individual pages are fine, but the database as a whole is now logically inconsistent and broken. Now, the single biggest threat, the thing that enables these dragons to attack, is that the operating system lies. It lies to your program. To make things feel fast when you ask it to write some data, it just quickly copies that data to a buffer in its own memory, immediately reports back success, all done, and then, maybe gets around to actually writing it to the physical disk later. If the power fails in that gap, poof, your successful write is just gone forever. You cannot build a durable system on top of a lie like that. So how do we fight back? How do we build something trustworthy on this shaky ground? We start by forging a shield. This is our first and most important line of defense, and its only job is to slay that first dragon, the torn write. We need a completely bulletproof protocol for writing and, just as importantly, verifying every single page that hits the disk. We do this by building a special component. We'll call it the file manager. Think of it as the one and only all-powerful gatekeeper to the disk. Nothing else gets to talk to the disk directly. And it offers a very simple but very powerful contract. When you ask it to read a page, it guarantees that page is not corrupted. And when you ask it to write a page, it guarantees that write is atomic and truly physically durable, not just sitting in some OS cache. So how can it possibly make those guarantees? Well, the magic is in the metadata we embed inside every single page. Before we get to the actual user data, we have a small header. And for now, the two most important fields in that header are the page ID, so we know we got the page we asked for, and a checksum. A checksum is basically a mathematical fingerprint of the data. If even one bit of the data changes, the fingerprint will be totally different. Okay, so here's the sacred ritual for writing a page. It has to be followed perfectly every time. 1. In memory, we compute that checksum, that fingerprint, over the page's data. 2. We embed that brand new fingerprint into the page's header. 3. We tell the OS, okay, write this page to disk. And 4. This is the crucial step. We force the write. We issue a special command like fsync, which basically tells the OS, stop lying to me. Do not return from this call until you can personally guarantee that every last byte is physically safe on the disk. It's slow, but it's the only way to get a real guarantee. The read protocol is just as paranoid. We fetch the raw bytes from the disk. We pull out the original fingerprint that was stored in the header. Then we calculate a fresh, new fingerprint on the data we just read. And finally, we compare them. If the new fingerprint doesn't match the old one, we know something terrible has happened. A torn write, bit rot, whatever. We immediately stop everything and raise a huge red flag. Look, a guarantee that you haven't tested is just a hope. It's totally worthless in the world of systems engineering. We can't just cross our fingers and hope our checksum shield works. We have to become the adversary. We have to actively try to break our own system to prove that it's strong. So we design a specific test. Let's call it Operation Torn Page. First, we use our nice, clean file manager to write a perfectly good page to disk. Then, and this is the fun part, we use a raw, low-level tool to sneak around the back, bypass our file manager completely, and intentionally scribble garbage halfway through that page on the disk, perfectly simulating a torn write from a power failure. The final step, we use our legitimate file manager to try and read that corrupted page. The test only passes if it catches us, if it screams corruption and refuses to return the bad data. Okay, let's take a deep breath and take stock of where we are. We've forged our shield, we've tested it against our simulated dragon, and it held. That's a huge step, but it's really important to be precise about what we've actually solved and what dangers are still out there. Now, a quick note for the pros in the audience. To really defeat the OS's lie, production databases often take it one step further. They use a special mode called Direct I/O. This basically tells the operating system, hey, I appreciate the help, but I've got it from here. It lets the database bypass the OS cache entirely and manage its own I/O. It's way more complicated to code, but it gives you maximum control and predictable performance. And our file manager is the perfect place to hide all that complexity. But all this safety, it comes at a cost, a massive cost. We call it the durability tax. Look at these numbers. An SSD might be able to do 80,000 writes per second if we just trust the OS cache, but the moment we add that fsync call, the moment we demand a real physical guarantee after every write, our throughput plummets to maybe a few hundred operations per second. That's a performance hit of over 99%, but that's the tax you have to pay for certainty. So what have we accomplished with our checksum shields? We've built our foundation. We've created the durable, verified page. This is now the bedrock of trust that the entire rest of the database can be built upon. We have officially defeated the torn write dragon. We can detect silent corruption, and we've hidden all this messy, dangerous complexity behind a nice, clean API. But, and this is the big question that should be forming in your mind, our shield is great at protecting a single page. We've slain the first dragon. But what about that second dragon, the partial write? What happens when a single bank transfer needs to update 2 pages, debiting from one, crediting another? How do we make sure that multi-page operation is also all or nothing? Well, that is the challenge for next time, when we move beyond the shield and forge our sword, the write-ahead log.